Alright, in this next step we are going to get the displacement due to the redundant reaction, which is ultimately our flexibility coefficient. Right, what we're going to do is we're going to apply not the redundant reaction but a unit value of the redundant reaction, and the displacement that goes in the same direction is that flexibility coefficient. Right, now we've got a whole bunch of stuff that's already been constructed here to help speed this along a little bit. Note that we've got this 1 unit load here. We have a 12-foot beam, a 12-foot high column, so the moment diagram for this situation is going to be then a linearly increasing moment that starts at 0 at the left end, increases to 1 times 12 for the max moment here. For the column, then we end up with uniform moment all the way along its length at also 12-foot kips. Right, again, our goal is to get this flexibility coefficient. Now when you draw this deflected shape for the frame that's consistent with the sketching rules for frames, note we've got boundary conditions at the lower right that are fixed for everything, so 0, so that curvature where we have compression on the right, tension on the left, so that we get this curvature that goes effectively to the right, the bending towards the right, we've got to set that up so that we have this curvature away from the original undisplaced position. We can't shorten the column, so that means that the displacement at the top of the column, the displacement due to the unit load, right, so the displacement is at B caused by the unit load being at A, then is entirely to the right. Now we're going to have a rotation that happens here, that theta at B caused by this rotation or unit load at A. That's going to be important to know because you're going to get that same rotation here and same rotation there, and that's what's going to allow us to get this portion in this right triangle, right, that this dashed line right here is the tangent of the at B for the beam extending all the way over, and that's going to tell us something pretty important about this component of FAA. The rest of this is the tangential deviation at A with respect to the tangent drawn back at B. Again, that being that tangent B being right there, and this being your theta B. Let's get rid of that little second subscript there. That's a little confusing. Right, so there's your little theta B that's going on. These are the values that we're going to need to get the FAA. So, and along the way, we'll also turn out that we want FBA. Right, so let's go back now and do some of these step by step. You've got this fixed end down at the bottom. That always makes things easier to work with. That we want this rotation right here, which is the same one as that one, and that's the same one as this one going from the tangent at A, or sorry, that's, oh, it's awfully confusing. This is down here at C. So theta B is going to be equal to theta B drawn with respect to the tangent at A, that change in that area. That's going to be the area under the M over EI diagram. That's going to be then 12 kip foot over EI times, right, so that's this portion, and it's uniform all across the height, so times 12 feet, and that's 144 kip foot squared over EI. Right, so that means this portion of FAA we've effectively almost just gotten here. We'll come back to that in just a little bit. While we're at it, let's go get FBA, the lateral displacement up here due to the bending of the column. That's just equal to a tangential deviation of B with respect to C. So that's that area, which is 144 kip foot squared over EI times that moment arm, and so that moment arm with respect to the point of interest is 6 foot. It's in the midpoint, and that will be 144 times 6, 864 kip foot cubed over EI. Note the units, one more length unit than we had for the rotation, so that's a good sign that we're doing things correctly. And then we come out, we're also going to need to get the tangential deviation at A with respect to B. Right, so that's going to be the first moment of this area up here between the 2 points. So that's 1/2 of a base of 12 foot times a height of 12 foot kip foot, either way you want to do it, over EI times a moment arm. That is going to be 2/3 of the 12, so 8 foot. And so that would be 8 over 2, that's a 4. 4 times 144 is probably 700 something. Well, no, it's not. What is it? 576 kip foot cubed over EI. So that finally we can come along and then say, okay, FAA, that's what we really were after here initially, is going to be equal to, well, opposite over adjacent is equal to tangent of theta b. So that's real small, so that's just equal to theta b times 12 will give us this little piece here. So 12 foot times theta b plus our tangential deviation of A with respect to B. Right? And we've got numbers for those now. That's 12 feet times the 144 kip foot squared over EI, plus what we just found out with tangential deviation of A with respect to B, that was 576. That isn't going to be the big portion of this at all. And so that will be total of 2304 kip foot cubed over EI for FAA. Right, from which their next steps are going to be, and oh, by the way, that would be up, wouldn't it? And that's going to be critical for the next couple of steps.